All right, welcome to calculating the pH of a weak acid, guys. This is something that you routinely will have to do. It's actually, I think you'll like this better than the usual equilibrium problems. These are actually a little bit simpler in my estimation. Just a couple of principles, and here we go. All right, this is a weak acid. This is acetic acid. It's going to ionize to a very small degree. It's a very reactant favored equilibrium. We can tell that it's reactant favored because the exponent is 10 to the minus 5 for the equilibrium constant. That tells us that we have very few products over here on the right hand side, and that most of our acid is going to remain as a molecules, and that's the way most weak acids exist in solution. They exist as primarily molecules. Well, actually, they all exist primarily. Here's our weak acid, our acetic acid, and so here's the way this is going to go. This is going to be ICE. We know that this is a 0.15 molar solution. The hydrogen ion concentration, it's actually not totally zero. If we account for the autoionization of water, we could have a concentration somewhere in the neighborhood of 10 to the minus 7 molar. But we're going to ignore any contribution that water makes to the hydrogen ion concentration. We'll treat it as a 0, and 0 here for acetate as well. Since this is all 1 to 1, this will be minus x plus x and plus x, and then we add 0.15 minus x, and then 0 plus x is just x. And this is our equilibrium line, same thing we had in chapter 15, only I think you're going to agree that the problem's a lot simpler. All right, we have a decision to make about whether or not this x is small enough to ignore. Now, I've already told you you're not going to have to do the quadratic equation on any exams. I'm going to stick to that even though the exams are online, and that might give it a little bit more complication. You're certainly welcome to do the quadratic formula to solve this problem, but in all the problems I'll give you, you can assume x is small. We can ignore it. So we're going to put together our equilibrium constant expression, which will be Ka is equal to H plus times A minus divided by the hydrogen ion concentration. And then we're going to substitute our values from the equilibrium constant expression. Our Ka, which is given in the problem, is 1.8 times 10 to the minus 5 is equal to x times x, which is just x squared, and then we'll divide that by 0.15 molar. To solve for x, which is the hydrogen ion concentration, that's what we're interested in finding out. We're going to multiply both sides by 0.15. It'll cancel over here, and 0.15 molar over here. So, and then we're going to have the x squared to take care of, so we're going to take the square root of both sides. So I'm just going to lay it out for you here. To find the hydrogen ion concentration for a weak acid, in all the problems that I'm going to give you, you can simply take the Ka, the square root of the Ka times the concentration of Ha, and that's going to give you the hydrogen ion concentration. So in this case, that's going to be the square root of 1.8 times 10 to the minus 5 times 0.15 molar. When I solve that, I get x, which is equal to the hydrogen ion concentration. Remember, this is just X that we're solving for. And that's going to equal 1.64 times 10 to the minus 3 molar in hydrogen ion. To get the pH is simply going to be equal to the negative log of 1.64 times 10 to the minus 3. Now, if you're really on top of things, you know that this is going to be a pH that's less than 3, because if this were 1 times 10 to the minus 3, the pH would be 3, but because it's a little bit higher, the pH is going to be a little less. And I'll just put it up here. The pH is equal to 2.78, and that is our answer. So that's how we calculate the pH of a weak acid given a sufficiently high concentration, a sufficiently low Ka, which it almost always will be for you, except perhaps on some homework problems where you have to do the quadratic formula. But on tests, no. And I don't think so on quizzes either. I'll have to take a look. But here we go. Just remember this formula and you will be good to go for weak acids.